So, Assalamualaikum warahmatullahi wabarakatuh. My name is NABILAH binti REZALI and my metric number is 214339. So for today, I would like to present question 1, which is a function fx, to show that function fx equal to square root x is uniformly continuous on 0 infinity but not satisfy the Lipschitz condition. So, by the definition, a function f is uniformly continuous on interval 0 infinity if for every epsilon greater than 0, there exists a delta greater than 0, such that in modulus fx minus fy is less than epsilon for every x, y element of 0 infinity when in modulus x minus y is greater than 0 and less than delta. So to show that fx equal to square root x is uniformly continuous, we need to show that for every epsilon greater than 0, there exists a delta greater than 0, such that in modulus fx minus fy less than epsilon for every x, y element of 0 infinity whenever x minus y is greater than 0 and less than delta. So the second step is we need to use conjugation for the square roots. So square root y minus square root x, we times with square root y plus square root x divide by square root y plus square root x. Then we get the answer is y minus x divided by square root y plus square root x. And third step, we need to let modulus x minus y is less than delta. Then y minus x divided by square root y plus square root x, we get in modulus x minus y divide square root y plus square root x. And to ensure that modulus square root y minus square root x is less than epsilon, we choose delta such that in modulus x minus y divide square root y plus square root x less than epsilon. And then we bring the square root y plus square root x to the right side, and we get modulus x minus y is less than epsilon times in bracket square root y plus square root x. So since delta is small enough, so we consider x and y are close, then square root y plus square root x is approximate to square root y or to square root x. And then we get the delta equal to epsilon times in bracket square root x plus square root y. By choosing delta equal to epsilon times square root x plus square root y, we ensure that in modulus fx minus fy less than epsilon. Therefore, fx equal to square root x is uniformly continuous on 0 infinity. So for the next step, we need to show that the function is not satisfy the Lipschitz condition on 0 infinity. And by definition, a function f satisfies a Lipschitz condition on an interval 0 infinity if there exists k greater than 0, such that in modulus fx minus fy less or equal to k in modulus x minus y for all x, y element in 0 infinity. So we write the definition as usual, fx minus fy less or equal to k times in modulus x minus y. And then we write the function in modulus square root x minus square root y less or equal to k in modulus x minus y. And as before, we get the modulus square root x minus square root y is equal to in modulus x minus y divided by square root x plus square root y. And as x approaches infinity, y approaches 0, so we get square root x plus square root y approximate square root x. And thus, in modulus, we get square root x minus square root y approximate in modulus x minus y divide square root x. Also, we get the approximate modulus x divide by square root x, and lastly we get equal to square root x. So since square root x grows without bound as x increases, there is no finite k such that modulus square root x minus square root y less or equal to k times modulus x minus y for all xy element of 0 infinity. So this proves that function fx equal to square root x is uniformly continuous on 0 infinity, but does not satisfy the elliptic condition on 0 infinity. So thank you.
So the next question of this step is let Sn be a sequence in F inverse F that converges to a point as element of M1. This means that for any epsilon greater than 0, there exists an n element of natural number such that D1 as n as smaller than epsilon for all n greater than n equals to n. Since f is continuous, we know that for any epsilon greater than 0, there exists delta greater than 0, such that the two fx, fy smaller than epsilon, whenever d1 sy smaller than delta. So let epsilon greater than 0, delta greater than 0. So there exists an n element of n such that d1 as ns smaller than epsilon for all n greater than n equals to n. Therefore, d2 fsn fs smaller than epsilon for all n greater than equals to n. So since f is closed, we know that fs element of f. Therefore, s element of f inverse f. For any sequence as n in f inverse f that converges to a point as element of m1, we have as element of f inverse f. Therefore, f inverse f is closed subset of m1.
So for the question number 3, it says that M1 and M2 be two matrix space, and our function M1 goes to M2. Suppose that our pre-image f power of -1, f is a closed subset of M1, and f is closed subset of M2. Prove that f is continuous on M1. When we want to prove that f is continuous on M1, we need to say that for every closed subset f of M2, the pre-image f-1, f is closed subset in M1. So how we want to prove? By 3 steps. So the first one is we need to define the definition continuity in matrix space. So we already said that M1 goes to M2 continuous if every open subset U subset of M2, the pre-image of f power of -1 U is an open set in M1. The second step is suppose that f subset of M2 is closed, then f-1, f is subset in M is closed to. As the definition, a set is open if and only if complement is closed. In here, we will say that U subset in M2 is open if and only if our complement, which is V equal to M2 complement of U, is closed. Our step number 3 is let U is subset in M2 open set, and then our V is closed set in M2. Since V is closed in M2, then our pre-image f power of -1 V is closed in M1. So we consider that in here we consider set of pre-image f power of -U is equal to M1 complement of F negative 1 V. Since our pre-image of V is closed in M1, then our complement M1 and F1 V is equal to F power of negative U is open in M1. So in here, we can make conclusion which is F is continuous if the pre-image of every open set U in M2 is open in M1. That's all. Thank you.
So next I will proceed with task 4. So the question asks if A is a closed subset of a compact matrix space M row, prove that the matrix space A row is also compact. So here I have listed down the steps on how to do this question. So firstly, we need to satisfy the condition of compact matrix space. So the first condition is we need to prove that the finite cover A subset of A alpha and diameter A alpha is less than epsilon is bounded entirely. And the second condition is we have to show that every Cauchy in A is converged to show that A is complete. Hence, the matrix space is compact. So firstly, I wrote let A be a closed subset of the compact space M row since we have got the information from the question. Next, since M row is totally bounded, so for every epsilon is greater than 0, there exists A alpha 1, A alpha 2 until A alpha n with diameter A alpha is less than epsilon. So when A is a closed subset of the compact space M row that is already compact, so we know that M is equal to A alpha I summation until n. So we know that A alpha is subset of M. So since we know that M is a compact, so we know that diameter of A intersect A alpha is less than epsilon. Hence, we know that A is totally bound. Now, to show A is complete, we have to show that every Cauchy in A is converged. So, we got A is a complete. So, here I wrote let xn is a subset of A be a Cauchy sequence. Same goes to xn is a subset of M be a Cauchy sequence. Hence, we get M is a complete. So, X is the element of M when n approaches infinity. So, every X contains infinitely many elements of Xn. So, it is same for A. So, every X contains infinitely many elements of A. Hence, X is the element of A. Since we know that A is a closed subset of A, so A is equal to A bar. Then Xn is convergent in A row. Hence, every Cauchy sequence Xn subset of A is convergent in A row. So A row is complete. So we have proved that by definition 6.5.1, A is compact.
For task 5, suppose f is a bounded function defined on closed bounded interval AB. If f is Riemann integrable on AB, prove that for every epsilon bigger than 0, there exists at least one partition P such that function UFP minus function LFP is smaller than the epsilon. Okay. For this question, we need to define the function, the f, and also give the partition and also show the bond to prove this question. First of all, suppose f is integrable on AB for every epsilon is bigger than 0. There exists partition P1 and P2 such that function LFP1 is bigger than LF minus epsilon 2 and function UFP2 is smaller than UF plus epsilon over 2. Okay. To show that P is equal to P1 union P2, we can show it as the given answer at the side. So after we show this, we can see that LF is equal to UF. So we can show the bound for this question, which is function UFP minus LFP is smaller than, for the function UF, we can change it to LF, because since from what we shown above, we can see that LF is equal to UF. So we can change it to LF plus epsilon over 2 and minus it with LF plus epsilon over 2. Okay. So after showing this question, after solving it, we can get the epsilon. So after answering this, we have proven that for every epsilon bigger than 0, there exists P such that UFP minus LFP is smaller than epsilon is proven.